11.8 linear programming, last section of the chapter. So we have a bunch of definitions here. So a linear programming problem in two variables x and y consists of maximizing or minimizing a linear objective function. Then it says z equals ax plus by. A and b are real numbers, not both zero. Subject to certain conditions or constraints expressible as linear inequalities x and y. Well, that's a mouthful. I'm not really sure what that means yet. So most of this I'm going to try to explain through some examples, through two examples. I do need to show a couple things in here. So solutions to a linear programming problem consist of a feasible point that maximizes or minimizes the objective function. So we're going to try to get a maximum or a minimum, and we're going to do this by basically solving systems to create these corners that we worked on, and the corners allow us to evaluate this function that is given to us. Okay, and to do that we're going to have to accept this theorem here, and that says that if you're dealing with a linear programming problem, and for example the last problem we did in 11.7 could be viewed that way, that was the problem that dealt with investing money, then the optimum solution or the minimum solution occurs at your corners. Okay, so let's look at what we have here, analyzing a linear programming problem. It says consider a linear programming problem, maximize I equals 0.05x plus 0.08y, subject to the conditions that, and so then they gave us all these conditions. Well, this is the problem that we worked on in 11.7. And then these represent so the 30 here represents $30,000. So that was this amount of money that the couple had, and so they were going to invest $30,000. And then the couple was going to invest $20,000 or more, and I believe the $20,000 or more was in the treasury bills. And then the couple was going to invest at most $5,000 in corporate bonds. And then the 0.05 here, that represents the 5% interest that the treasury bills yield, and the 0.08 represents the 8% interest. So we graph this problem, and from that problem, so this is the problem from 11.7, we were able to find the following corners. So I don't want to regraph the whole thing. I just want you to sort of get an idea of how this works after you graph it. So we had corners that were given by those coordinates. Okay. This is then where we're going to use this equation. So this equation depends on an x and a y. Well, that's what we have here. We have x's and y's, right? With this is the x variable, and here's the y variable. So we're going to plug in these values, and we're going to see what I would be worth. So I stands for the interest. So the interest would be, in the first situation, 0.05 times 20 plus 0.08 times 5. And if you do that, you would have a total of 1,640. So this is what was the amount of interest that would be earned. If you do this with 20-0, it's a little bit easier, and you can clearly see that 20-0 would be less. So that would be only $1,000 of interest. And then here, when we use the 25, and then when you use 0.08 times 5, you end up at 1,650, and then the last one would be times 30, that's 1,500, then here times 0, and that would give you 1,500. Now, I'm not saying that 0.05 times 20 plus 0.08 times 5, that's not 1,640, but this problem was given in thousands of dollars. So the answer here was actually, it must be 1.64, and then I multiplied. So the reason I did it sort of an easy problem here is that I want you to see that this equation here that we're trying to maximize, that's what's called the objective function. That's the function that ties into the linear programming problem. Now that particular equation is not being graphed. You don't have to graph it. The values that you find for x and y are the corners of the system. Then you plug that in. So in this case we have a maximum right here, and the minimum would occur if you use this combination of values. Okay, so that's sort of a little bit of background. So we'll do the whole thing now. So that's the procedure. Let's look at the procedure. It says write an expression for the quantity we maximize and minimize. That is the objective function. Then write the constraints. Those would be the less than or equal signs or the greater than or equal ones. Find the corner points, and then plug those corners into the function, the objective function, and see what happens. So here we go. Factory manufactures two kinds of ice skates, racing and figure. So, lost my marker, there we are. So I'm going to call those R's, and the figure skates I'm going to call F. The racing skates require 8 hours of work. So I'm going to start writing some things down. So the racing thing require 8 hours, and that would be 8 hours of work in the fabrication department, in fabrication. And the figure skates require 4 hours of work. Okay? Both of them require 2 work hours in the finishing. So in finishing they need 2 hours, and these need 2 hours. So I don't know if I'll need this, but that would mean it takes 10 hours to produce a set of racing skates and 6 hours to produce a set of figure skates. Okay? What else do we have? The fabricating department has available at most 224 work hours. Well, that means that 8 hours times the number of racing skates plus 4 hours times the number of figure skates has to be less than or equal to 224. The finishing department has no more than 72 hours, so this would be less than or equal to 72, and each of these would require 2 hours of work. So that's a set of constraints that I have. Let's see, what else do we really need? Well, nothing from there. And then it says if the profit on the racing is $15 and the profit on the figure skate is $12, how many of each should be manufactured each day to maximize profit? So here's the objective function. The profit comes from $15 times the number of racing skates that you make and $12 times the figure skates that you make. So we need to come up with a system for that, and we're going to graph that. So I have some straight lines. So on this axis, I'm going to call this is the y-axis. So this would be figure skates. The racing skates will be here. And now I need to plug this or plot this. So what do I have? So let's work on this one first. So if I say that, I'll use a little bit of different color here. So if I say that the number of finishing skates is 0, so I'm going to basically treat this as a linear equation while it is. If F is 0, then the number of racing skates would be 224 divided by 8. So the number of racing skates would actually be 28. So 28 would be a point over here. Now I can't graph it yet because I don't know how much else we have. I can also do this the other way. If I say the number of racing skates we make is 0, then the number of figure skates would be 224 divided by 4. So that number is significantly larger, and that's 56. So I need to go up to 56 here right now. This one's a little easier if both of these would be equal to each other. So if R is 0, then you can have 36F. So 0 and 36 is a point, but so is 36, 0. So hopefully this makes sense. So this is the point 28, 0. And this point was 0, 56. Okay, so the biggest number I need to graph over here is 56, and the smallest and the biggest number that I need to graph over here is 36. So what do we got? So 10, 20, 30, 40, 50, 60. 0, 56, if that's 50, so there's a dot there. And then that connects to 10, 20, 30, 40, that connects to 28, so that would be over here. So that's one line. And we have a second line, do that in a different color. And that would be at 36 on this axis, so that would be 0, 36, so 10, 20, 30, 36 would be about right there. 36 would be right here for that. It's about the halfway point. And so both of these were going to be a less than or equal inequality, right? So to the downside here, and the same thing with the blue one. So the blue one would be below as well. So here is the region that we're really interested in. So all possible solutions come out of this region. Okay, so my corners are pretty easy to spot, and most of those actually, oh, that's the wrong order. So this was the point 28, 0. And this y-intercept is 0, 36. And then I still need to find this. So that I need to find by equating both of these. So I need to solve 8r plus 4f equals to 224. And at the same time, 2r plus 2f equals to 72. Divide by 2 is here, so you would get r plus f is 36. And then we're going to just solve this for r. So r is 36 minus f. And I'm going to put that into there. So then I get 8 times 36 minus f plus 4f is equal to 224. 8 times 36 would be 288 minus 8f plus 4f is 224. That's a negative 4f over here. That's a negative 64. So f would be 16. If f is 16, 36 minus 16 is 20, and r is 20. So the coordinates here are 20 and 16. Okay, that's a lot of work. Well, not too bad. And then we can finalize. So now I can finally start to use this profit function that I have over here. So I'm actually going to take that and take that with me for a second. I'll make it move over here. So I need to work on that. So we're going to plug in the points that I just found. So I'm going to plug in 0, 36. Well, that's easy, right? If you plug in, so you get 15 times 0 plus 12 times 36. So that would be 15 times 0 and 12 times 36, that's 432. If I plug in the points, so I started up here, so 2016, plug in that point, so it would be 15 times 20 plus 12 times 16. So when I do that, I get 492. And then the last point I need to plug in is 28,0. So 15 times 28 plus 0, and 15 times 28 is 420. So the combination that maximizes profit is the 20 and 16. So the answer to the final question is, how many of each should be manufactured each day to maximize profit? We should make 20 racing skates and 16 figure skates. And that's it. Thanks.